This is the second video in a series on mastering resonance. In the first video, we reviewed the concept and we also looked at some basic guidelines or rules. In this video, I'll present some common structural patterns which are related to resonance. By recognizing these patterns, you will more easily anticipate the existence of resonance forms. A common theme with all these patterns is that they involve delocalized pi electrons. So in our first example, we're looking at an allelic lone pair. So allelic refers to the situation where you have a pi bond, and so I'm going to point to the pi bond right here. There is next to this pi bond a lone pair of electrons on an adjacent atom. So the lone pair that I'm thinking about is the one right there. So that's an example of an allelic lone pair. Notice we also have a lone pair up here, but that lone pair is nowhere near a pi bond. We can anticipate a resonance form by using our curved arrows, showing the lone pair move down to, in a sense, form a pi bond, and then the electrons in this pi bond coming to be deposited on this carbon. Again, I'm implying some sort of movement, when in fact there is no movement at all, just further representation of the single structure. So now if we draw the second resonance form, it would look something like this. As we've mentioned before, there should be a conservation of charge. So now the nitrogen and the carbon both have charges, but collectively they add up to, in a sense, being neutral. So that's the example of the allelic lone pair. The allelic positive charge is again the situation of having a pi bond and then on an atom next to the pi bond, in this case we have the positive charge, not the lone pair. So we're talking about, of course, that positive charge. We can explore looking for resonance forms using our curved arrow. So in a sense, we show the pi bond shifting to the other set of carbon atoms, and the subsequent structure or resonance form would look like this. We've seen these resonance forms before. We're just bringing them in under the category of allelic positive charge. The next pattern that we're looking for is a lone pair next to a positive charge. And so here we have an oxygen, and it has two lone pairs. It doesn't matter which lone pair you pick, and I'm going to imagine the lone pair as, in a sense, making a pi bond and thereby completing the octet for the carbon. The resulting resonance form would look like this. Note there's a conservation of charge. Now in the first two examples, I'll just come back here, you can easily see that they indeed involve pi bonds and in a sense delocalized pi electrons. In this third example, at first you don't see a pi bond, but indeed the result of these delocalized electrons, there is a pi bond related. And so these electrons we would say are delocalized. By contrast, the other pair of electrons are localized, and we'll say more about that in the next video. Finally, if you have a situation of a pi bond between two atoms of different electronegativity, so here we have a pi bond where we've got a carbon and an oxygen. Clearly, they differ in electronegativity, and the oxygen, of course, attracts the electrons more strongly. And so we can look for the second resonance form using our curved arrow and showing that the pi electrons, in a sense, also exist up on the oxygen. And so the next resonance form that we can draw would look like this. We've seen this before, and so once again we have the carbon lacking an octet, having a positive charge, the oxygen having the extra electron, therefore a negative charge. Overall, the charge is conserved. We can summarize these four examples on the following chart. Actually, all resonance forms to some degree can be described by these various patterns. To give you an example, I'm going to pull out an example that's found in the homework further on in the page, and this comes from the question number 2. And I realize that you don't have a lot of room, but see if you could sketch this down. And at first, when you look at it, you may think, oh, this particular example does not include or is not part of the 4 other patterns that we've talked about. But if you look a little more closely, and for instance, if we start just here, we can see that what's happening is this is a pi bond between two atoms that differ in electronegativity. And so if we then draw the subsequent resonance form, which would look like this, we can see that in fact what we have is an allelic positive charge. And so I can look now for my next resonance form by bringing the pi bond down here, and then here's my next resonance form. And you can see indeed the positive charge is distributed both on the carbon below the oxygen as well as on the last terminal carbon. The two arrows that you see in the leftmost structure actually imply those three different resonance forms. In a sense, it's kind of a shortcut. Finally, let's do a little bit of practice. So you'll see in key question number 1, these three different structures. I ask you to stop the video and to try to draw the subsequent resonance form. You'll see that these three structures will match one of the 4 different patterns that we've talked about. Be sure to use the double-headed arrow to imply the connection between the next structure that you're drawing. Okay, so I hope you stopped the video. Now if you look at the responses, here are the corresponding resonance forms. I will use curved arrows in each case to look at how we might find these. And so I'm going to use a lone pair of electrons on the oxygen. So this would be an example of an allelic lone pair. If I bring the lone pair down in a sense to form a pi bond and then use the electrons from the pi bond and bring them onto this bottom carbon. The subsequent resonance form has a positive and a negative charge. So in a sense, there's a conservation of charge, overall neutral. In the next example, I have the situation of a lone pair next to a positive charge. And so I can, in a sense, look for a pi bond, note that there's a conservation of charge. Both structures have a positive charge. And then finally, I have an example of an allelic positive charge. So there's a positive charge next to a double bond. And so indeed the distribution of that positive charge is both on the carbon in the ring as well as the carbon coming off the substituent. In the next video, we'll see the consequence of having delocalized electrons on hybridization.